My dear students, let me welcome you all to a new edition of physics. In this edition, I'll resume revising the first 3 chapters. You will be encountered with very interesting questions, multiple choices and problems. So let's get started. Okay, the first question here, we've got a diagram that shows the change of the EMF induced by a coil of a dynamo. Your attention, yes, please pay attention to the figures given. The time on the x-axis, on the abscissa, is given in milliseconds, so it must multiplied by 10 to the power of negative 3. And we want to calculate the periodic time of one cycle. Yes, it is 20. Or we can use the formula, periodic time equals number of cycles over, yes, we want the periodic time over cycles. Time over cycles. For example, 10 over half cycle, or 20 over half, or 30 over 1.5. But we have to convert it into millisecond. Time of one cycle is the periodic time, or the tau. The figure shows the variation of the electromotive force generated by a dynamo coil, a coil of a dynamo that revolves at an angular velocity omega. Okay. What about the question? Find the frequency of rotation. Frequency is the reciprocal of the periodic time. It is the reciprocal of the periodic time. Cycles over time. Okay, it is 1 over periodic time 20 times 10 power negative 3. So it is 50 cycle per second or 50 hertz. It's all easy, clear-cut question. But still we have something interesting. Still talking about the same diagram. We want you to draw a diagram to represent the change in the EMF generated in the coil of the dynamo, yes, over 20 milliseconds, when the angular velocity is doubled. And instead of being omega, okay, it will be twice 2 omega. And we want you to draw it once again, assuming that we've increased the angular velocity. We doubled it. Can you do it? Yes. What is the effect of doubling the frequency? Okay, we should show in the diagram doubling the frequency. Doubling omega means doubling the frequency. It is 2 pi f. And when the frequency is doubled, EMF generated will be doubled. So we have to interpret this on the diagram we'll draw. Okay, so in front of you, this is the first diagram, and compare it with the second diagram. In the first, we've got just 1 cycle, and in the second, we've got 2 cycles. This happens when omega is doubled, because frequency is doubled. And maximum EMF was 100. In the second diagram, it will be 200. So notice the difference between the 2 diagrams. When you are asked to redraw it, assuming that angular velocity is doubled. Okay, this is very interesting. We've got another type of questions, and it is very important, and you will show it, you will be given to you in a multiple choice. What about the title of the question? Okay, when does each of the following quantities equal 0? The torque acting on a current-carrying coil carrying an electric current and placed in a uniform magnetic field. We want you to tell us when, in what position, the torque will be equal to 0. We've got 2 positions. Okay, talking about the torque and talking about the dynamo. Vertical position and horizontal position. Horizontal position, where the plane of the coil is parallel to the field, yes, what happens? Torque is maximum. And EMF generated in the coil of the dynamo is maximum. But in the vertical position, where the plane of the coil is perpendicular to the field, torque equals 0. Also, EMF induced in the coil of the dynamo equals 0. So the question asks for, when does torque equal 0? We'll say in the vertical position. Torque equals 0 in the vertical position, where the plane of the coil is, yes, perpendicular to the magnetic field. Is perpendicular to the magnetic field. We'll explain it. Since torque equals BIA and cosine theta, so torque will be equals 0 when theta equals 90. So the plane of the coil must be perpendicular to the magnetic field. Okay, this is quite clear. Still talking about the same type of question. When does the magnetic flux at any point inside and along the axis of a current carrying solenoid equal 0? We've got a solenoid and carries current, okay, but magnetic flux at a point inside it is equal to 0. Okay, this happens when? Thank you very much. When the solenoid is made of a doubly wound coil, okay? Okay, in this way, current flowing in one branch will be equal and opposite to that. So the two fields will be equal and opposite. They cancel out. We don't have any field inside the solenoid. When? When the solenoid is doubly wound, made of a wire which is doubly wound. Okay, when does the magnetic flux at any point inside and along the axis of a current carrying solenoid equals 0, okay? When the solenoid is made of a doubly wound wire. Still talking about the same type of question. When does the EMF induced in a wire that moves in a magnetic field equal 0? We've got a wire, and the wire is moved in a magnetic field. We expect it to cut the magnetic flux lines, and we then have an EMF and current flows. Okay, but we didn't have any current. Okay, so the wire must be moved parallel to the field, no cutting. The wire must be moved parallel to the field. Okay, so the answer, when the wire is moved parallel to the field, once again, using the formula, the expression, mathematical expression, okay, EMF induced equals to BLV, B magnetic flux, density, L length of the wire, V linear velocity, sine the angle. Okay, so EMF equals 0 when theta equals 0, because sine 0 equals 0. Still talking about the same question. Theta, of course, theta is the angle between field and direction of motion. Theta, okay, equals 0. When does the force of a magnetic field on a current carrying wire equal 0? So what is the situation now? We've got a wire, current carrying wire, placed in a magnetic field. The wire produces a field, and we've got another magnetic field. They'll interact, and we expect the wire to move, but it didn't. Why? Can you tell? Yes, it is placed. Okay, the wire is placed parallel to the field, so no interaction. Okay, okay. The wire must be placed parallel to the field. Using the formula, the force equals BIL sine theta. Force equals 0 when theta equals 0, because sine 0 equals 0. Okay. Another interesting question. When does, your attention please, the difference between EMF of a cell and its terminal voltage, the difference equals 0? Will you please try to think over this question? When does EMF, the difference between V battery and terminal voltage equals 0? It means when does the terminal voltage equals V battery. This happens in two cases. When the main circuit is broken, no current passes through the battery, through the cell, or the internal resistance is theoretically neglected. Okay? So, once again, when does the difference between EMF of a cell and its terminal voltage, yes, equals 0? When the circuit of the cell is open, that's to say the resistance across the terminals of the cell is infinite. No current passes through the cell. This is one case. Okay, and when the internal, another possible, yes, reason, internal resistance of the cell, yes, is neglected, is equal to 0. Okay? Still talking about the question, same question, when does the average EMF induced in a coil, okay, in a magnetic field, okay, we've got a coil, and the coil is rotated in a magnetic field, and average EMF is equal to 0. Okay, this is, you should know it by heart. It happens in two situations. When the coil completes one revolution starting from the vertical position, when it completes one cycle starting from the vertical position. Also, when it completes a half cycle starting from the horizontal position. So the answer, when the coil completes one cycle starting from the vertical position, and the other possible case, also when the coil completes half cycle but starting from the horizontal position. Talking about the same question, when does the magnetic flux density at the midpoint between two wires, yes, equals 0, two straight wires. This happens, okay, when the two wires carry currents in the same direction, carry currents of the same intensity in the same direction, okay. When the two wires carry equal currents in the same direction. One last thing. The current in the primary coil of a transformer, in spite of its connection to an AC supply. You know, the transformer, yes, consists of primary coil and secondary coil. The primary is connected to the mains, okay, but no current can flow through it. Can you tell why? Yes, because the secondary coil is broken. Okay, it's an open circuit. This happens when the secondary is a broken circuit. Okay, the current in the primary coil of a transformer, in spite of its connection to an AC supply, equals 0 when the secondary circuit, secondary coil, is open. A backward, at this point, a backward EMF is induced in the primary coil, which is roughly nearly equal to the EMF of the supply. So no current flows in the primary coil. Another type of question, draw a labeled diagram to show the construction of the moving coil galvanometer. Then mention the function of the hair coils in the device. Let me say it again. Draw a labeled diagram to show the construction of the moving coil galvanometer. Then mention the function of the hair coils in the device. Okay, in front of you, yes, it consists of a coil that's wound around, and of course we've got a pointer that moves on a linear scale. The coil attached to the coil, a pointer that moves on a linear scale. Linear scale means it is equally divided. And the coil pivots on jewel bearings and hangs between two curved poles produced by a permanent magnet. Okay, this is the construction of the moving coil galvanometer. Okay, so once again we've got a fixed soft iron, and around it, wrapped around it, a coil that pivots in jewel bearings, attached to it a pointer that moves on linear scale, and we've got hair springs. And the question, part of the question was about the function of the hair springs. What about the function of the hair springs? It has, or they have, three functions. They produce an opposite couple. They produce an opposite couple which balances the electromagnetic couple. Okay, this is the first. They bring the coil and pointer back to zero scale to rest position when cutting, when finishing, measuring the current. Also, they lead the current in and out. They lead the current in and out of the coil. Okay, another question. Choose. Okay, this is the most important type of question. This is the type of question you will be encountered in your exam. Okay. First of all, when a small resistance is connected in parallel to the coil of a galvanometer. When a small resistance is connected in parallel to the coil of a galvanometer, the sensitivity of the galvanometer decreases to 1/10 of its original value. Decreasing the sensitivity of the galvanometer means something very important. It means it has been changed, converted into a meter, okay, to measure higher currents. Maximum current, full-scale deflection of the galvanometer is denoted by Ig. Current denoted by the ammeter is I. So I equals 10 Ig. This is given. Okay, so when a small resistance is connected in parallel to the coil of the galvanometer, sensitivity of the galvanometer decreases to 1/10, means I equals 10 Ig. Decreases to 1/4, I equals 4 Ig. Decreases to 1/3, I equals, yes, 3 Ig. Okay, now we want the ratio between shunt resistance and resistance of the galvanometer. It is equal to 1/3, 1/4, or 1/9, or 1/10. Quite clear it is, the answer it is equal to 1/9. How we managed to know it? I'll explain it. The shunt resistance of the shunt is given by IGRG over I minus Ig. But we've got a piece of information I mentioned, which is, thank you very much, I equals 10 Ig. Substituting, yes, for I, so shunt resistance equals IGRG over 10 Ig minus Ig. 10 Ig minus Ig, 9 Ig. Okay, so IGRG over 9 Ig. Ig will be crossed out, so quite clear it is, the ratio now is 1/9. A galvanometer can be modified, another choice, a galvanometer can be modified into an ammeter by connecting its coil in parallel to a small resistance called shunt resistance. Let me say it again, a galvanometer can be modified into an ammeter by connecting its coil in parallel to a small resistance called shunt. Okay, do you know one of the functions of the shunt is to decrease the total resistance of the device? It means the resistance of the ammeter is smaller than that of the galvanometer and is smaller than that of the shunt itself. Okay? Yes, what about the choice? The ratio of the resistance of the ammeter produced, okay, to that of the added shunt. Okay, is it greater, equal, or less? I've just explained it. When connecting to a shunt, will decrease the resistance. So the device produced will have a resistance less than that of the shunt. So the right choice is less than. Okay, thank you very much. I believe it is interesting. When a resistance, okay, this is very, very important question, very important choice. When a resistance of 1200 ohm is connected to an ohm meter, the pointer of its microammeter deflects to half its full scale. I'll say it again. When a certain resistance is connected to the ohm meter and it shows deflection to half its full scale, know it for sure that the ohm meter has a resistance equals to 1200 ohm, is equal to the added resistance. So I've already learned a piece of information here, which is resistance of the ohm meter is equal to 1200 ohm. This happens when the pointer deflects to half its full scale. When we add this resistance, when we add a certain resistance, and pointer of the device deflects to half its full scale, we know for sure that the resistance of the ohm meter is equal to that added resistance. So resistance of the ohm meter equals 1200 ohm. What about the choice? Wait. Okay, the resistance which makes the pointer of the microammeter deflect to a quarter of the full scale of the current. Okay, this is very interesting and intelligent. Is it 600? Yes, 1800, 2400, or it is 3600. Okay, it is 3600, but how I managed to know it? Okay, stay with me, please, because this is very important, a choice. As I said, resistance of the ohm meter is equal to 1200. Okay. Second resistance equals, yes, 1200 times 4, because the pointer deflects to 1/4. So the resistance must be increased 4 times as great as previous. Okay, it will be, stay with me please, 4800. So the new resistance of the ohm meter after adding an external resistance equals 4800, and it was 1200. So I must add 4800 minus 1000, yes, 200, it is 3600 ohm. So important a choice. Okay, another choice, a galvanometer is of resistance 27. The shunt resistance, which increases its range 10 times, I believe I've just explained, one which is very close to it, very similar. Yes, increasing the range 10 times means I equals 10 Ig. Okay, is it 2.7, 3, 9, or 10? Of course it is 3. It will be divided by 9. Okay. Another choice, the maximum value of an AC current is 10 ampere. The frequency of the current is 50. Your attention please. Okay, when solving problems on AC currents, we'll use the effective value. We don't use maximum value. So 10 should be converted into its effective value. How? It is multiplied by, yes, 0.707. Then we can use the current. The current actually is not 10, it is 10 multiplied by 0.707. Frequency equals 50, so periodic time 1/50. And we have a resistor 100 ohm. Okay, what about the choice? The electric energy consumed through the resistance, is it 707 joule, 99.9, yes, 4998.5, or the last choice, 1000. What formula to be used? I squared RT. But remember, I should be effective value. Resistance is given. And what about the time? Time, yes, in one cycle, it is one of the frequencies, periodic time. In this way, it will be 99.97 when you calculate it. Still doing choices, multiple choices. The instantaneous EMF induced in the coil of a dynamo, AC dynamo, starting rotation from zero position is given from the relation, the expression, EMF instantaneous 220 sine omega t. What about 220? 220 is the maximum EMF. Okay, what about the choice? The average EMF induced in the coil during its rotation through a quarter of a cycle is 220, 140, or is it 345 or 0? It is 140, but the question how you manage to obtain it. We've got a relation that relates average EMF and maximum EMF, and it is important to memorize it, okay? Yes, average EMF equals maximum EMF times 2 over pi. Okay, maximum is given, yes, 220. When multiplied by 2 over pi, it will be the figure I chose. It is 140 volt. Okay, another choice. A factory gets its electrical power from a generator 2 kilometers away. The two wires connecting, your attention. A factory gets electrical power from a generator. It is 2 kilometers away, and we've got two cables to connect current. Two cables, this is very important. The two wires connecting the generator to the factory terminals have a resistance 0.03 ohm per kilometer. Per kilometer, and the distance is 2 kilometers. So it should be multiplied by 2. And for two cables should be multiplied by another 2, and we'll get what we want. Okay. When the generator supplies 50 ampere to the factory, the terminal voltage at the generator is 120 volt. Current 50, voltage at the generator 120. Okay. We want the voltage at the factory. Voltage drop. Okay. How to do this? The choice will be, yes, 114. And I'll explain it. We'll calculate the drop in voltage. Okay. How to calculate the drop in voltage? Voltage equals IR. But there is a trick here. Well, what trick we have here? As I said, the voltage at the factory terminals equals voltage at the power station minus drop in voltage or loss in voltage. Voltage at the station 120. Your attention, minus 2, because the distance is 2 kilometers. Multiplied by another 2 because we've got two wires, one going and one coming, and the resistance was 0.03. Okay, it will be 114 volt. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Stay blessed, stay safe. Thank you very much.